Applications of trigonometry. We're all experts in trigonometry now. The first application is the area of a triangle. This is a very nice simple formula, as simple as ABCs almost. Given side angle side measures in a triangle. This formula works from trigonometry. Well, you're given side A, side B, and the included angle gamma between the two of them, right? When you're taking the triangle, you're given A, B, and here's gamma between them because it has to go opposite C, right? How can you find the area of a triangle? We can already do it, right? Here's what you can do. You can drop a perpendicular here. Call this height H. You can use trigonometry to find the height H, right? Because, right, you have if you're given an angle and a side of a right triangle, you can solve the whole triangle. And for instance, you can find a side and angle. You can solve for the another side. And then once you have this, the right triangle area is easy, right? 1/2 base times height. And this one, similarly, you can figure the base by solving again 1/2 base times height. But that takes a long time, right? You have to drop the perpendicular, find the perpendicular using right triangle trig, and find this one using right triangle trig. Sorry. Then you got to take 1/2 base times height. It's not too bad, but there's a faster formula that we can derive from that method. What we can do is this, is say the area as drawn is 1/2 base times height, but instead of going through and computing all that, we'll say, what is the height? On this triangle here, a right triangle, we notice that the sine of the angle is h over a, opposite over hypotenuse, right? Which multiplied through by a becomes equivalently a times sine gamma is the height. So here I'll take 1/2 base times a sine gamma. And what I've done is I've taken this method of dropping the perpendicular and got a short formula for it. What I've got is a theorem in any triangle given the lengths of sides A, B, and the measure of angle gamma between them, the area is equal to, I'm going to reorder this, 1/2 AB sine gamma. There it is. Now I said this is almost as easy as ABCs. Do you see it? The other way of labeling these sides and angles is opposite A, you put alpha, opposite B, you put beta. Over here, you put C opposite gamma. And what happens in other books, we use alpha, beta, gamma for the angles, is we'll instead use C for the point at gamma, and we'll say this is angle C, and then this will be point A, and this will be point B. We don't want all those in the diagram, but they'll call it angles A, B, C instead of alpha, beta, gamma. So if you use the other prescription, then it's 1/2 AB sine C using the other angle. So this is the way I remember it, because otherwise, if you don't use it for it, forget it. It's right, 1/2 AB sine C is the formula. It's very easy. Also, by nothing more than relabeling the sides. All right, so maybe B is here and C is here. We can write that area is 1/2 BC sine alpha, or A is 1/2 AC sine beta. It's just like the law of sines and the law of cosines. There's 3 of them that are all equivalent just to labeling. So I'm going to call this one the superstar. And that's the one I'll use all the time today because I remember ABCs a lot easier than I remember BCAs and that kind of stuff. Right? And what we want to do now is given any triangle, instead of having to write down a bunch of geometries, write down the formula. So for example, suppose I have a triangle. If A measures 18 inches, B measures 32 inches, and the angle between them, gamma, is 40 degrees in a triangle. The area is A equals 1/2 A B sine C, or gamma. All right? And I can run all those quickly on my calculator. And I got 185. If these are inches, then area has to be square inches, recall. So 185 square inches. Okay, it's as easy as that. Here's one more formula though. So try the homework on that, just AB sine gamma or AB sine C. Another formula is not trigonometry. It dates back to an ancient Greek. Put the overhead here. It's kind of fun just to see the history of this, really. This is some artist's rendition of Heron, an famous ancient Greek. You can look this, also called Hero of Alexandria, Heron of Alexandria. Did all sorts of things. He's a famous mathematician and engineer. He built a steam-powered device. How about that? Long before we came up with steam-powered engines. He's remembered mostly for Heron's formula that we're now going to write. It's another way to find an area of a triangle when you're given side data. So you can look that up on Wikipedia and find out about that, about him. So another formula is due to the ancient Greek Heron. And it's this theorem. Maybe I should say, and it's for side data given. You're given all three sides. Anybody own a farm, right? If you had a triangular farm, you can measure off maybe on the road along the sides here, or with your tractor coming down the aisles around the edges. And suppose you measured sides A, B, and C of a triangle, and that's all you knew. You didn't know the angles because you can't see over the trees and crops and so forth. How many square units, square miles or whatever is your piece of land? All right. Well, you can figure it out by a fast formula. Again, since you have side, you can use the law of cosines to solve the triangle. And once you have that, you figure 1/2 base times height with a lot of work. But this formula is faster, is what it is. Given side, here's the formula Heron came up with. I think this is amazing for someone from his time to come up with this. This says in any triangle with sides A, B, C, given S equals what? A plus B plus C over 2 gives the area formula A equals square root of S times S minus A times S minus B times S minus C. This one has so much symmetry. This one isn't too bad to remember either. I want you to memorize both of these equations, right? So this is our second star equation. And you need this to be able to compute it. There's how to get an area of a triangle given side data. You compute S and then plug it into this formula. And that's it. Heron got such a nice formula. I guess he's a good engineer. Huh? So now we can find one of those. I'm going to do a curve here, right? They say life throws curve. This is what you might get in real life. Maybe your plot isn't really a triangle. Maybe it's a parallelogram. Let's see if I can find the page here. I don't have it. All right, so find the area in square miles of the parallelogram with side lengths say A equals 4.2 miles and B equals 2.5 miles. Suppose you have a piece of land that's like that. How many square miles is it? With a rectangle would be easy. You just multiply A times B, right? Base times height, and you'd have it. Here's what a parallelogram is, right? A parallelogram is a quadrilateral, a plane object with 4 line segment sides that has parallel opposite sides. So that's parallelogram. So this side parallel, this one's parallel, this one. This necessitates that the opposite sides are the same length. These are both A and these are both B. So if I give you A and B, you know all 4 sides. Now, what's the area of a parallelogram, I wonder? Kind of hit on this one, how we can find the area of a parallelogram from a triangle formula. Feel free to interject online if you have a comment. What you can do is draw a line down the diagonal here, right? And this is a triangle, and this is a congruent triangle, right? Because it's A, B, C, if you like. A, B, C, side is a congruence theorem. So these two triangles are congruent. They have the same area, same measures, and therefore the same area. And so what I can do here is use Heron's formula to find the area of this triangle. Sorry, this was going to be for the other formula, wasn't it? Well, let's go ahead and do this one. And then find the area of the whole thing by itself. So let's do this. What's the length of side C down the middle? We know from I think this is okay, so we can find the length of the diagonal here first. See if I can remember the trick on this one now. I was starting this out as a different way. Yeah, I didn't give enough information. That's what happened. I need the diagonal here. So side lengths and the diagonal. So suppose that C is equal to 5.0 miles. All right. Now we're going to say that by Heron's formula, if we compute S is equal to the A plus B plus C over 2 is 4.2 plus 2.5 plus 5.0 all over 2. Let's see, we've got 9.2, 11.2, 11.7 over 2 is 5.85 miles. All right. So I've got S, and now we can compute with Heron's formula. The area is square root of S, which is 5.85. And here's what I want to recommend on the homework. This S times S minus A times S minus B times S minus C, I tend to make a lot of mistakes trying to put in all those parentheses. I always get something wrong. Sometimes what's easier to do is just compute S minus A, S minus B, S minus C separately, especially if you can do it in your head. Like for instance, what's 5.85 minus 4.2, right? It's 1.65, so I'll just do that subtraction in my head. What's 5.85 minus 2.5? Well, that's 3.35, right? So this is a times 3.35. And then times what's S minus C? 5.85 minus 5 is 0.85. And so I'll do the subtractions in my head. I actually tend to be less mistake-prone when I do that in general. Now I just got straight multiplies without all those parentheses. I compute this as square root 5.85 times 1.65 times 3.35 times 0.85 and get 5.24. What's wrong with that? Yeah, this is the area of the triangle. So this is the area of the triangle. And now you want the area of the parallelogram is what we asked for. Will just be twice 5.24. We'll put one more digit. 5.243. And get 10.49. So there's the area of the parallelogram. So there's a twist. You want to find the area of a parallelogram, given two edges in a diagonal, you can do it by finding the areas of both triangles. That's all there is to that. There's no trigonometry in this one, but we presented at the same time, just with the idea that we did the other area formulas, trigonometry. Let's do the alternative area formula. Now you know how to find areas of triangles quickly, whether you're given side angle side or side data. If you're given something else, then you can use log signs or cosines to get side angle side or side, and then solve it a little longer. All right. I think that's all I'm going to do on areas of triangles. That's the first application. It's pretty easy. You've got two formulas, the 1/2 AB sine C formula and the Heron's formula for the side angle side and side cases. Next application is polar coordinates. These we're going to take a little longer on. These are used extensively in all sorts of science and engineering classes because these are very convenient when you have some sort of a radial symmetry, anything that has circles in it, or pieces of circles like pizza, right? If you got a slice of pizza because it's a sector of a circle, right? It's a slice out of a circle. Those are very convenient in polar coordinates. These kind of things are described much more easily with equations. Here's how polar coordinate works. we'll say recall first Cartesian coordinates, also known as rectangular coordinates. Cartesian means they're named after Descartes, one of the early mathematician philosophers who started using these. In Cartesian coordinates, you can take any point on the plane and drop a perpendicular to the x-axis, right? This is Euclidean geometry. Each point, one of the axioms in there is that you can has a unique perpendicular to the line not through the point, or on the point that is the same on the line is the same point. And a unique perpendicular over here, if this one intersects at x and this one intersects at y, then we'll say that the coordinates of this point are x, y, and that ordered pair identifies the point, right? It's the one that has perpendicular drop to here and perpendicular drop to here. That uniquely identifies the point to write an ordered pair of numbers. Sometimes to get a better symmetry for problems with circles and so forth, and sectors, you want to use an alternative coordinate system. These are our Cartesian coordinates. Alternatively, polar coordinates, which we might see today when the tornadoes come, if they do, because they're really radar coordinates, right? What you do is you take the distance from the origin out to the point, and we call that r. So what is r? It's the square root of x squared plus y squared, right? By the Pythagorean theorem. After all, this is x and this is y. Then this is square root of x squared plus y squared. This is the distance from the origin. Now, if you also take the angle counterclockwise from the positive x-axis and call that theta, here's where the trigonometry is coming in, right? Then the ordered pair r followed by theta also identifies the point. The way people usually do is they turn the angle first and then go out the distance. So if you give me an ordered pair like pi over 3, 2, then I will turn to this angle pi over 3 and go out 1, 2 units and find that point that way. So instead of finding the point by saying going out 2 on the x-axis, 3 on the y-axis, or 4 on the y-axis and seeing where they converge, instead I'll turn the angle and go out the distance. So that's polar coordinates. How will we convert between these polar coordinates and xy coordinates if we're given a system in one? Trigonometry to the rescue, right? Because this is a right triangle, right? We can go back to right triangle trigonometry, and we notice in this diagram that x over r is adjacent of hypotenuse cosine theta, and y over r is sine theta, and y over x is tangent theta, right? All those things can be used to convert. For instance, if I take the first one and multiply it through by r, I get x equals r cosine theta, right? Let's multiply this one by r. Now, if I'm given r and theta polar coordinates, radar coordinates, turn to here. Radars actually go clockwise, but we'll go counterclockwise for positive measure. If I turn to the angle theta and go out the distance, I want to know what, and I've given r and I've given theta, I can convert to xy by saying x is just r times cosine theta. From this pair, r theta, polar coordinates, I can get this pair, xy. Y then, by multiplying this one by r, is r sine theta. So there's the conversion from polar to rectangular coordinates, just like that. So if you give me the two numbers, r and theta, I can convert and get the two numbers xy to identify the point the usual way. Now, how can I go the other way? I could write the Pythagorean theorem. Here I wrote the Pythagorean theorem solved for r, but I would say x squared plus y squared equals r squared is the Pythagorean theorem. And from over here, right, tangent is opposite over adjacent, y over x. So I write tangent theta. Oops, I should have written this in the other order. R squared equals x squared plus y squared is the usual way. And then tangent theta equals y over x. And these two equations can be used to solve for polar coordinates given rectangular, right? If you want to find r, you just take x squared plus y squared, that's r squared. You can square root it and get r. You take y over x, then you take r tangent plus pi, depending what quadrant theta is in, and get theta. So this will convert given XY coordinates to R theta coordinates. Find out what's the angle you turn through and what's the distance you go out. Alas, it's not quite so simple. It's almost that simple. It's not too bad. There is an alternative that's real convenient in applications. You'd say, why do you want to do this? It makes it more complicated. It's for the applications, really. We can also allow in polar coordinates R negative. What you do now is here's a point up here with coordinates x, y again. Instead of taking the distance to the point here to be r, I'll take that distance to the point to be minus r. So r will be negative. R is minus the square root of x squared plus y squared. All right. So distance minus r is the distance to the point. R is minus the distance to the point. Maybe I should write it that other way. But anyway, so this is the distance here. So r is negative, and then if r is negative, what we're going to do is take this angle theta. And what do you know about this angle theta? Opposite directions always have the same tangent, right? If I take y over x here, I can also go here to the point minus y and minus x here. And this ratio, minus y to minus x, the minuses cancel. You get the same ratio as this. This angle here has the same tangent as this one. So this one also satisfies tangent theta equals y over x. And if you square this, this also satisfies r squared equals x squared plus y squared. All right. So you notice actually in both these prescriptions here, I should write it over here, by the Pythagorean theorem, r squared is x squared plus y squared. In both these prescriptions, r squared is x squared plus y squared, and tangent theta is y over x. So we'll just say these are the equations for both cases. So we'll call this equation 1, x equals r cosine theta, y equals r sine theta. Given polar coordinates, r theta, you can get rectangular coordinates x, y. And then equations 2 will be given x, y, you can find polar coordinates r theta. The trick is you just have to figure out which quadrant theta is in and whether r is negative or not, right? And the idea is that if you're going to choose r, you can choose it either way, right? These are both allowed as it is. You can choose to turn to it, you can choose r positive, in which case theta has to turn to the direction of the point, same quadrant as the point, and then you go out that distance, or you can choose theta to be the opposite direction to the point, the opposite quadrant, and go backwards. Absolute value of r when r is negative. So if r is positive, you take theta to the point. If r is negative, you take theta the opposite angle away from the point. That's what you do. And you can choose r to be either plus or minus the distance to the point. Now we need some examples because it's complicated. So that's the idea. Polar coordinates or radar coordinates, turn the angle and go out the distance. Or you allow this other thing where you go turn to the opposite direction and back up the distance. Oops. So suppose I said convert the polar coordinates 2 minus square root 3. I'm sorry, minus 2 plus square root 3 to rectangular coordinates. Cartesian coordinates. It's all both. All we need is equation 1. So if you're going from polar to rectangular, it's actually very easy. Just put x equals r cosine. Oops. Wrote this wrong. Polar coordinates minus 2 pi over 3. Sorry about that. Minus 2 pi over 3. X equals r cosine theta is minus 2 cosine pi over 3. Now y is minus 2 sine pi over 3. And we just compute on the unit circle what the sine and cosine of pi over 3 is, right? We actually do it with a, since it's first quadrant with a triangle instead of the unit circle. But we'll say on the unit circle, this is square root of 3 over 2, and this is 1/2 for an angle of pi over 3. So the cosine is 1/2 and the sine is square root of 3 over 2. This is -2 times 1/2. And this one is -2 times square root of 3 over 2. So the rectangular coordinates are -1 minus square root of 3. All right. So there's the rectangular coordinates for that point. What did I do there? Here's the picture. I found this point, -1 minus square root 3, if this is -1 and -2, square root 3 is about 1.7, right? And so we want to be right here, -1 minus square root of 3, those are the rectangular coordinates. And what I did there was I turned to the opposite direction because r is negative. There it is. So I'll turn to the angle pi over 3. And then I'll back up by the absolute value of r. I'll back up 2 units. So I'll go out this direction, 1, 2 units, and there it is. There's the point with polar coordinates, -2 pi over 3. Turn to the angle, and when r is negative, back up that many units, 2 units in this case. And it's precisely the point with rectangular coordinates, -1 minus square root of 3. Okay, so it's converting to polar. Is all you have to do is just take this number times cosine of this number for x, this number times sine of this number for y. Nothing more to it than plugging in. But the picture is more complicated as far as negative. Well, suppose we said this. Let's convert the other way. Convert to polar coordinates given rectangular coordinates. Suppose the rectangular coordinates are -2 square root of 3. Now I convert those to polar. Well, now I'll use, if I'm going rectangular polar, I'll use equations too, but they're tricky because r squared is x squared plus y squared. R can be either plus or minus the square root of this. And then tangent theta equals y over x can be in the direction of the point xy or the opposite direction. Okay. So let's choose r positive. If r is positive, then what I get is r is plus the square root of x squared plus y squared from equation 2. So we'll use 2 to convert from rectangular to polar. Is the square root of -2 squared plus square root of 3 squared. Not what I wanted. This is supposed to be -1 square root of 3. I want to make the numbers a little easier. -1 square root of 3. So it's -1 squared plus square root of 3 squared, and now it's square root of 4 is 2. Right? So that's the r positive. If I want r positive, then also I want tangent theta equals y over x in the same quadrant as the point, which is quadrant 2, right? And if r is negative, I want to take it the opposite quadrant, quadrant 4, excuse me. So if tangent theta is y over x, I can figure this one out exactly because these come from a special triangle, right? So tangent theta equals square root of 3 over -1. Remember how to solve tangent theta equals a number? You can divide top and bottom by the root sum square and call it square root of 3 over 2 over -1/2. And now this is y and this is x. Or it could be minus this one and plus the other one. And this could be y and this could be x. Which one is it? If I want quadrant 2, then I want x negative and y positive. So we choose this one. And on the unit circle now, we can go to minus a half plus square root 3 over 2 to get this point. And the idea is the actual point is further out here. The actual point is in the same direction. This is minus 1 square root 3, just twice as far out in this case. But we get this point right here, if I drew it well enough, where this is square root 3 over 2 on this side, and this is 1/2 on this side, and this is 1. Oh, it's a 30, 60, 90 triangle. This angle must be 2 pi over 3, because this angle is 60 degrees, pi over 3. So we deduce that the angle here is theta equals 2 pi over 3 from the unit circle. Now I've got r equals 2, theta equals pi over 3. The polar coordinates are put r first and then theta is the order, just like you put x before y, it's just convention. 2 pi over 3 are polar coordinates for that point. That's polar coordinates with r positive. The homework's going to ask you now find polar coordinates with a negative, because like I say, people do use those. All right? What are corresponding negative coordinates with r less than 0? How about that? Remember? For r less than 0, you just take minus the distance to the point. So instead of 2 units, not 2 units, you put minus 2, right? The distance to the point was 2. Here was the idea, was that too close of all these numbers. Here was the picture of the unit circle. We're going to the point minus a half square root 3 over 2. An angle 2 pi over 3. The actual point is 2 units out, r equals 2, at that same angle, minus 1 square root 3. So we can turn angle 2 pi over 3 and go out 1, 2 units and get to the point with rectangular coordinates minus 1 square root 3. The alternative is let r be minus this distance, so r equals minus 2. And then what I need to do is turn to the opposite direction, this direction. So what direction is that? Well, I can just add pi to the other coordinates. 2 pi over 3 plus pi takes you to the opposite side. That's 5 pi over 3. So if I use r negative, I have to choose the opposite direction, 5 pi over 3. Or if you prefer, you could choose minus pi over 3. That's the same direction. So here's 2 polar coordinates, one with r positive, 2 units out, turn to the angle that goes to the point, 2 pi over 3. One with r negative, you take minus the distance point, minus 2 units, and turn to the opposite direction, 5 pi over 3. Okay? Now I'll ask you a tricky question. What are all polar coordinates? These are 2, one with r positive and one with r negative. What you find, unfortunately, with polar coordinates, it's not like Cartesian coordinates where each ordered pair, there's only one ordered pair for each point, right? If you give me a point in the plane, I drop the perpendiculars, there's only one ordered pair it can be, following Euclidean geometry. But polar coordinates not so. There's actually an infinite number of polar coordinates for each point. One of them has r equals 2, theta equals 2 pi over 3, but all coterminal angles take you to the same point, right? If I turn the same direction by going 27 rotations around and in here, it's still the same point I'm going to get to by going out r units. So if I add k rotations, how do I do that? I k times 2 pi in radians, or it's usually written this way, 2k pi. So that's k rotations, and it can be any integer. K equals 0, 1, minus 1, 2, minus 2, etc. Any number with nothing after the decimal point. So those are all polar coordinates with r positive. What about r negative? I take the one that I have, minus 2, 5 pi over 3. and I take all coterminal angles are gotten by by adding 2k pi, right? K rotations plus or minus. And these are all polar coordinates because these are all angles with that terminal, with the correct terminal ray for R positive and for that terminal ray with R negative. And then put R equals the distance or minus the distance to match it. So there's an infinite number of polar coordinates running over all the integers. I want to make one additional note. What points have R equals 0? R is the distance from the origin or minus the distance from the origin. So if R is 0, you're at the origin, right? R equals 0 is at the point at the origin, but in polar coordinates, it's called the pole. So we'll just change the name from origin to pole, although you can use origin, everybody knows what you mean. With theta arbitrary, right? Because it doesn't matter what angle you turn. If you didn't move out from the origin, it's still the origin, right? So at the pole, there's actually even more infinitely many points. You can take any angle you want. Just put R equals 0. All right, so that's how you get infinitely many polar coordinates for each point. But fortunately, once you give me polar coordinates, it only identifies one point, right? Because I just turn to the angle and go to the distance, or turn to the angle and go back to the distance, depending on whether R is positive or negative. Now we can try this. Suppose I'm given polar coordinates. Three pi over 2. 3 pi over 2 puts you on an axis, right? You can do the same conversion equations. These equations won't always work. One works, but what's easier? Easier is just to imagine in your head what it looks like. 3 pi over 2 is a quadrantal angle. It lands you between the quadrants. And then 3 puts you out 3 units. 1, 2, 3. So there's R equals 3. What is the rectangular coordinates to that point? 3 units down in the negative y direction, then this must be minus 3. So I get the rectangular coordinates, Cartesian coordinates, are 0, minus 3 without a calculation. So if it's a quadrantal angle, lands on one of these axes, then don't do R cosine theta or sine theta, just imagine it and come up with it, right? Similarly, if x equals 0 or y equals 0 in rectangular coordinates, that's going to give you a quadrantal angle, and you want to imagine it to get the polar coordinate. So if I say convert rectangular coordinates, 0, let's say minus 4, 0 to polar, this is very easy, right? You don't have to do the calculation. Because this is a quadrantal, because this lies on an axis, it gives you a quadrantal angle. You just go to the point 1, 2, 3, 4. This is rectangular coordinates. Here's the point minus 4, 0. And you imagine in your head, well, if this angle, the straight angle I know is pi, and it goes out 4 units, so R can be 4. So I choose the angle to the point, then I have to choose part R positive. I say polar coordinates are 4 pi. There's polar coordinates for it. Or if you want choose R negative, then you choose minus this distance, put minus 4, and the angle theta equals 0. That's opposite. But you don't have to do any calculation. Again, you see how far out it is and put an angle that puts you on the axis. Then you can add 2k pi to either of those, of course. All right. one last case here. Not always do you get special angles, right? Suppose I said to convert out of this nice 3, 4, and 5 triangle, the rectangular coordinate minus 3, 4 to polar coordinates. How can I do that? The nice thing I did here, since I set up a 3, 4, 5 triangle, we won't get nasty numbers in rectangular coordinates. 1, 2, 3. 1, 2, 3, 4. I like to picture this in my head. It really helps me. You don't have to do this. But we're talking about this point here with coordinates minus 3, 4, right? I wonder what r and theta are for that, right? So I could let, just to be simple, let's choose r to be positive. What is r? For r greater than 0, we erased it. By equations 2, we know that r is the square root of x squared plus y squared. The square root of minus 3 squared plus 4 squared, and square root of 25 is 5. This point is 5 units from the origin. Now, what's the angle? That's the hard part. Since this is not a special angle, we just go straight to the equation that tangent theta equals y over x is 4 over minus 3. What could theta be? There are always two angles theta that have a given tangent, right? I mean, two directions theta. One is to the point, one's in the opposite quadrant in the opposite direction. Then you can add 2k pi to either if you want. But one solution is theta equals the arctangent of minus 4/3. What's the other one? The other one is directly opposite, right? So I can add pi or subtract pi. It doesn't matter, just so it points opposite. Subtract 3 pi if you want, right? Arctangent minus 4/3 plus pi. Let's put we add it. Which one is it? Since we've chosen to make r positive, we want theta to go into the quadrant that we're in. Whether you would look at the diagram, this is why I like to draw them. The point is in quadrant 2. With r positive, I have to use theta in quadrant 2. R was negative, then I have to choose it in quadrant 4, the opposite one. Which one is in quadrant 2? Well, you can run the arctangent till. Inverse tangent minus 4 divided by 3 gives me minus 53.13 degrees. Well, wait a minute, that's down here. That's in quadrant 4. So that's not right. And since I'm doing degrees, I'll call this plus 180 degrees, right? Be careful when you're calculating, right? If you do this arctangent in radians, you want to add pi, but if you're doing degrees, you want to add 180. Otherwise, you'll be adding radians and degrees, it'll be garbage, right? So we want this one, arctangent minus 53.13 plus 180. I got 126.87. So we can say polar coordinates for this, if I use degrees, are 5, 126.87 degrees. So there's when you have a non-special angle. You just use arctangent or arctangent plus pi, whichever one puts you in the quadrant you need for the point. Getting harder. Every new topic starts off with a couple simple things. Those first diagrams are easy, but when you start getting to these non-special angles, it starts to get more difficult. Okay. Now we also want to convert equations. Oh, actually, let's do one more thing. I need to do for that sketching polar coordinates, right? In rectangular coordinates, how do you make a sketch? You can use graph paper, right? Graph paper with straight lines. Because each straight line is corresponding to holding one of the two coordinates constant. All right, so if we have, here's x and y. Have 1, 2, 3, 4, 1, 2, 4. And if I say plot a rectangular coordinates, the point 2, 3, then I march 2 along the x-axis along this straight line and 3 along this straight line, and I get it right there, right? 3. 1, 2, 1, 2, 3. And I get there. We can do a similar thing with polar coordinates, right? We just have to turn the angle in and go out to the point. Now these, if you look, this is the line x equals 1, x equals a number. This is the line x equals 2, x equals a number. Here's x equals 0, the axis. Here's y equals 0, y equals 1, y equals 2, y equals 3, right? Horizontal lines. But you get lines when the coordinates are constant. Similarly, in polar coordinates, you consider curves along which the polar coordinates are constant. So similarly, in polar coordinate, what does a curve r equals 1 look like? What kind of curve is that? R is the distance from the origin that the point is, right? You turn to R and you go out of R, or if the R is negative, then it's minus the distance. But this says that you want the point, all points 1 unit from the origin. So the set of all points 1 unit from the origin is the circle of radius 1, right? It's the unit circle. All points 1 unit from the origin. What if I put r equals 2? This says all points 2 units from the origin. It's the circle of radius 2. Etc. R equals 3 is the circle of radius 3. And we can keep going. And so if we plot curves of constant r, just like we put curves of constant x and y here, curve of constant r will be circles. We can put r equals 0 here if we want. R equals 1, r equals 2, r equals 3. And we can label these 1, 2, 3, 0. And so there's curves of constant r, or circles instead of lines. Now what about theta? What if I put theta equals, we'll do this for r greater than 0 only. For r greater than 0, what if I put theta equals pi over 6? What is that? This is a ray at angle pi over 6, right? Counterclockwise from the x-axis. Yeah, okay. And so I turn to an angle pi over 6, and if r isn't negative, then I just can go out as far as I want like that. These are all points theta equals pi over 6. If you pick a point like 2 pi over 6, then I turn to pi over 6 and go out 2 units. You pick the point with the polar coordinates 3 pi over 6, I turn to pi over 6 and go out 3. So these are all points with arbitrary r and theta equals pi over 6. So you get rays. And then here's another one. Theta equals pi over 3, right? Here's theta equals pi over 2, the y-axis, right? Turn to 90 degrees and go up. Here's theta equals 2 pi over 3. And you just label them without theta. Here's 5 pi over 6. Here's pi. 7 pi over 6. 4 pi over 3. 3 pi over 2. Some polar graph paper will label more than these angles, but 4 pi over 3, 5 pi over 3, excuse me. and 11 pi over 6, and theta equals 0. So there's what you can do. You can label the rays with the corresponding theta. We can now erase theta. And you label the circles with the r values. And now you can plot points. So we plot points by turning to theta and going out r. And we can also do r negative by turning to the opposite direction and going backwards, absolute value of r. So we plot polar coordinates. Write that down by turning to angle theta and moving out forward r if r is positive, or backwards absolute value of r if r is negative. So here, let's try this one. Plot the polar coordinates. Have to say what they are, otherwise it's a pair of numbers that could be either x, y, or r theta. Plot polar coordinates. A 2 pi, 2 pi over 3. What do I have to do to that simple one? I do the angle first as usually. I turn to 2 pi over 3 this way, and I just march out 2 circles, or 3 circles. 1, 2, 3. So here it is, right there. It's that one. Right? Suppose I wanted to plot 3 13 pi over 3. How about that one? That's a big angle, but you can say, oh, that's the same direction. So I subtract out a multiple of 2 pi. So 12 pi over 3 would be 4 pi. I could call this 4 pi plus pi over 3. In other words, 2 rotations plus pi over 3. So I'm going to go around twice, but then I'm going to go to pi over 3. So I'm going to go this direction. And now I go out 3 units. 1, 2, 3, and there it is. So you find the coterminal angle. This is 2 rotations. And this is the coterminal. You turn to the coterminal angle as marked and go out whatever r is. Now C, I could try going r equals -2 and theta equals 5 pi over 6, for instance. What do I do with that one? Now it's tricky because r is negative, right? You turn to 5 pi over 6, the angle, but instead of going out at 5 pi over 6, you go backwards 2 units, 1, 2 to here, right? And so that's that one. It's very funny. It looks so easy on the board, but I always have people miss these on the test, so I'm going to make sure I do it on these. Suppose I gave you -1 and minus 5 pi over 4. How about that? That's a little tougher because 5 pi over 4 isn't marked on there. But what we can do is we can say, remember from the beginning of the course, minus 5 pi over 4 is minus pi over 4 more. So it's, right, a straight angle and a 45-degree angle. So I'm going to turn, and negative is clockwise. So I go around pi. Then I go pi over 4 halfway between these. I should call it minus pi and minus pi over 4. I guess since I'm going clockwise. So I'm going to be halfway between these two things. And now I want to go out 1 unit in the opposite direction. So instead of going out this direction, I go backwards 1 unit. And I wind up on the r equals 1 circle here, right there. There it is. The point. See how I can trick you on this? It's halfway between these two rays here because it's a 45-degree angle instead of 30 or 60. And I went clockwise and then backed up. All right. So there's sketching. Finally, we have to do some equations. Often what's convenient about this is use both equations 1 and 2 when you're converting equation 2. We said before, if you're given r and theta polar coordinates, just use equation 1, it's easiest. If you're given rectangular coordinates, just use equations 2, it's easiest. Where this is 1, x equals r cosine theta, y equals r sine theta. And 2, the equation that works for both r positive and negative was r squared equals x squared plus y squared. And tangent theta equals y over x. And you just have to figure out what quadrant theta is supposed to go into and whether you want to choose r positive or negative, then choose theta to be the right quadrant to go with it. All right. So when you're converting equations, what's best is to use either or both, whatever makes your conversion nicest. But try and get your equations so you have not theta, but tangent theta or cosine theta or sine theta. You want to get one of these conversion quantities, not something in between. Here's a classic example of something that comes up a fair amount. You'll see it if you take calculus, for instance. Suppose you want to convert this one. To rectangular coordinates. I give you an equation of polar coordinates, and suppose I want to sketch it. Here's my equation. The equation for, like y equals x squared is a parabola. Here's a polar equation. R equals cosine theta. I wonder what figure that is. Don't do this. Say, I'm going to choose r positive. Therefore, I'll take square root x squared plus y squared. But it doesn't say r is positive, so I can also choose minus square root x squared plus y. Then I've got to say, oh, it's cosine of theta, but theta is evidently arc tangent y over x or arc tangent plus pi. So I don't know whether to add pi or not. Who can solve all these different cases? Add pi or don't add pi, positive or negative, and figure out what quadrant it's in. That's a mess. Don't do that. What you want to do is get in the form where you use 1 or 2 directly. So here's where the homework comes in. This is the one you have to practice because you'll get on the test and just sit there and not know what to do if you haven't practiced. It's not enough to memorize the equations, right? You have to have imagination. So you multiply this by r and say this is equivalent to r squared equals r cosine theta. Now look, r squared is here, I can convert it directly. R cosine theta is here, I can convert it directly. So the rectangular coordinate equation is just x squared plus y squared by equations 2 on the left, and x on the right by equations 1. So on this, when you're converting equations, you use both or 1, whatever's convenient, right? And there it is. Here's the equation of rectangular coordinates. All right. So that's how you do that one. Just multiply through by r, and then you can see how to substitute directly. Don't do this. Now, moreover, we'd like to be able to sketch it because we know how to sketch lots of things like lines and circles and parabolas and so forth in polar and rectangular coordinates. We don't know so much in polar coordinates, except r equals a number as a circle and theta equals a number as a line. What about sketching this one? Actually, okay. So here's how you can sketch this one. You put it into this form. We'll say this is equivalent to x squared minus x plus y squared equals 0, right? By subtracting x from each side. And this is a trick. So to sketch, we're going to have to put it in the form we recognize. Do the following. Now I'll try and complete the square on here. How do I complete the square? Remember that means make this a square or something. What you do is you take 1/2 of the number that multiplies x, it's minus 1, and square it. Minus 1/2 times minus 1/2 is 1/4. That's what I need to add here to make a square. Now this will be something squared. Remember that from completing the square in algebra? Thought you'd never use it again because you had the quadratic formula, didn't need to complete the square in equations. You need to complete the square in this equation. Well, I can't just add 1/4 on the left side, I'll change the solution. So I'll balance it by adding 1/4 on the right. There I go. Now this one is x minus a half squared. It's always half of this number. Plus y squared equals 1/4. And what's that? Maybe you recognize it. All right, 1/4 suggestively is 1/2 squared. That's a standard equation for a circle. Remember circles from algebra geometry? X minus x0 squared plus y minus y0 squared equals r squared is always a circle. At center, x0, y0 of radius r. You memorize this formula in algebra. So this is a circle at 1/2, 0, right? Because it's subtracted 1/2 here, but 0 here. Circle at 1/2, 0. Radius, this number, 1/2. Now I can sketch it because I've converted to rectangular coordinates. I plot this point in the center, 1/2, 0, and make it radius half so it just touches the origin, and there it is. This circle here is the graph of r equals cosine theta. How about that? Remember this equation for circles? I want you to recognize this for the test. But this is just the square of the distance formula. If you put square root of each side, you put square root of this equals r. That's just the distance from xy to x0, y0. If you take an arbitrary point xy. Distance between an arbitrary point and the center of the point, x0, y0, is equal to r. If you square the distance formula, that's the standard equation for the circle. That's where it comes from. So know this circle equation. That's going to come up in at least one of the homework problems. Then you can sketch these things. Let me give another tricky one. There's different ways. The object is by hook and by crook, be able to get these common equations into where you can use these two here directly. Example, this time convert a different one. R equals 4 secant theta. How about that? Instead of sine, it's secant or cosine. Excuse me. R equals 4 secant theta. What does that look like? If I multiply by r, that doesn't help me, right? I get r squared. That's nice to convert, but I don't know how to convert r secant theta. That's not up there. So what I do instead is rewrite this equivalently as r equals 4 over cosine theta and multiply by cosine theta. Then I've got r cosine theta equals 4. Now I can convert directly. I don't want cosine theta, I want r cosine theta because that's in the equations. This is now by direct conversion by 1. I only need 1 this time. X equals 4. Oh, it's a vertical line, right? X equals 4 is all coordinates, x equals 4. I can plot that immediately without any more thought. 1, 2, 3, 4. It's this line right here. Right? All lines with coordinate x equals 4. Suppose I have r equals -2. I wonder what the graph of r equals -2 is. Can you think what that is? This is actually a circle of radius 2. R equals a constant is always going to be a circle of radius absolute value that constant. Here's how you think of it. Imagination is sometimes more important than being able to write the equations on these. R equals -2. Remember, R is plus or minus the distance from the origin. This says all points that you go to an angle theta and go the opposite direction 2 units. 1, 2. And so if you let theta be arbitrary, because theta is not restricted there, you go around the circle of radius +2. So r equals a negative number is a circle of radius positive that thing. That's the way to think about it. All the points at a distance 2. Here's how to prove it with the equations. You square both sides and get r squared equals 4. Now you've squared both sides, you can use these equations directly. R squared is equal to x squared plus y squared. So this is x squared plus y squared equals 4. What is that? That's of the form x minus x0 squared plus y minus y0 squared equals r squared, right? If I count 4 equals 2 squared, let's write it suggestively. It's a circle of radius 2 at 0, 0, because I subtracted nothing. Circle, radius 2. So just what we figured here from imagining, right? At 0, 0. There's the proof by equations, if you prefer, right? So r equals 2 and r equals minus 2 are actually the same circle, right? And this justifies the squaring because technically when I squared both sides of the equation, I got new solutions, right? R equals minus 2 instead of all points before. R squared equals 4 means r might be 2 or r equals minus 2. And now I have both those solutions, but they're the same circle. So we say actually these are equivalent equations, even though there's solutions with r positive here now. It's the same circle, so it's the same point set. So we say these are actually equivalent statements for the point set, even if there's new solutions r, they're the same points. So there's that kind of trickiness in there. When you square both sides, you can introduce new solutions, right? So check them, make sure it's the same curve. But that's what you do. You try and get it by hook or by crook into one of these equations, and then check you didn't introduce extra solutions when you did that. Let's do one more. Suppose I have the equation theta equals a constant. We talked about plotting that before as a ray when r is greater than 0. That's good intuition. Suppose I put theta equals 7 pi over 6. We already have intuition, well, more than intuition. It's all points at an angle 7 pi over 6. But if you think about it, you can let r be positive and go in this direction. You can also let r be 0 and get the pole, or r be negative and go in this direction. So we expect it to be the whole line. That's one way to figure it. If you do the equations, how do you convert this? You can take the tangent of both sides and say tangent theta equals tangent 7 pi over 6. Right? And tangent theta, however, is in the equations. It's y over x. So now we have y over x equals tangent 7 pi over 6. Or equivalently, by multiplying by x, y equals tangent 7 pi over 6x. What's that in rectangular coordinates? This is just a number, right? In fact, we can figure tangent 7 pi over 6 is right here. The tangent is minus 1 over square root 3 if we figure on the unit circle. This is y equals minus 1 over square root 3x. What's that? It's y equals mx plus b, right? It's a line of slope minus 1 over square root 3 and y-intercept 0. Any equation y theta equals a number is always a line of slope tangent to that angle through the origin. So that's just what we thought here, exactly. Just we didn't know the slope. Now we know the slope, m, is minus 1 over square root 3 because of the equation. So this is a line of slope minus 1 over square root 3 through the origin or pole. Is what you get when you put theta equals an angle, a fixed angle. It's just a line of slope tangent that angle through the origin. All right, let's try these then. We did a bunch of stuff today, didn't we? A bunch of applications. That triangle section is short. Out of 8.2, yeah, 8.2, we want to do some triangle problems now. 5 is Heron's formula. And then 10, also 6. Now let's just do 5 and 10. There's Heron's formula, and there's the 1/2 AB sine C trigonometry formula. Then 8.3 do all of them. I think it's 1 to 7 on polar coordinates. There's not so many, and they're all really good exercises. Yeah, 1 to 7. All right. Thank you, everybody.